everyone. So welcome to our regular PCS seminar. So today's speaker is Jun-Won Rhim from a fellow IBS Center for Correlated Electron Systems at SNU in Seoul, and he's going to talk about quantum distance and anomalous Landau levels of flat bands. So Jun-Won received his PhD from Yonsei University in 2011, and then was working at KIAS, University of Toronto and Max Planck Institute for Physics of Complex Systems in Dresden, and since 2017 he's a research assistant professor at the Center for Correlated Electron Systems, and his research interests are centered around topological aspects of solids and strong correlations. So let's welcome our speaker. Juzar, that's for you too, the applauding sound.
Thank you, and thank you for a very nice introduction. And today, as the organizer introduced, I will talk about some new physics in the flat band systems, and it's a very unexpected relation to the quantum geometry called quantum distance. And today's my presentation is based on my 3 recent papers published in these journals shown here. Okay, so this is my contents of a talk. So after a very brief introduction to the flat bands, and I will say my motivation in this flat band business, and I will quickly show my most important results on the Landau levels of flat bands first. And because to understand this new behavior, we need some understanding on concepts like singular flat band and the quantum distance or pseudo-spin. So I will then, after introduce those 2 concepts, and then I will explain how to understand the anomalous Landau levels of flat bands from these perspectives. Okay, so let me start with very brief introduction. So the band structure is the collection of eigenenergies and corresponding crystal momentum, as you all know. So this is about solids. Before atoms form a solid, they are disconnected to each other. So at each atom, we have the same eigenenergies, E1, E1, E2, E3, like this way, with discrete energies in every atom. So if we plot all the possible or allowed energies as a function of a crystal momentum, we have this flat band already. This is very trivial case of a flat band. Actually, we are not interested in this kind of flat band systems. So if we allow electrons to hop between atoms, we have some mixing between orbitals at different atoms, and it will make some kind of bonding or anti-bonding energy levels very roughly, and it will make the flat band of the atomic levels make warped like this with a finite bandwidth, where the bandwidth is roughly proportional to the hopping parameter between those atoms. So basically, if we plot band structure of the solid, we usually obtain finite bandwidth and some dispersions between energy and momentum. So this is the usual cases in solid states. And in the band structure, we can extract very useful information like group velocity of some carriers made of electrons in this single band, which is the first derivative of the energy as a function of a momentum. So it tells us how fast the carriers in the bands are. And another information is the effective mass, which is inverse of the second derivative of the energy as with respect to the momentum, and it tells us how heavy the carriers are in a band. So when the band is flatter and flatter, we say the charge carriers in such a band is heavier and heavier. Okay. So in usual cases, this is the most well-known simple case, the two-dimensional square lattice. We have this kind of very well-known cosine-shaped band structure. This is very dispersive. And in graphene, we have a linear dispersion at the Dirac point, like this. This is also a very well-known example. And we can see that at the Dirac point, there's a band crossing or band touching between two bands, upper and lower bands. And this degenerate point we call band crossing or band touching. Please remember this terminology, because I will talk about this concept quite often in the later part of my slides. Okay, this is the usual shape of the band structure. But in some very special cases, like Kagome lattice, we have a very strange band structure called the flat band. This is the Kagome lattice, which is very similar to Japanese basket called Kagome. So this is why we call this as Kagome lattice. And this lattice system is quite popular in the business of frustrated magnets. But that is the case when we include electron-electron interactions. But without electron-electron interaction in this band theory level, it is still very interesting because it has a flat band at the bottom of the whole band structure. And this flat band is touching with the upper dispersive band at the gamma point. So the key properties of the flat band is that group velocity is equal to 0 because the first derivative of energy with respect to the momentum is 0. And the effective mass is infinite because the inverse of the second derivative is diverging at every momentum. So these two characters are the key features of the flat band. Please remember this one. And this kind of Kagome lattice is very special because in this band structure, we actually assumed that the hopping is only for the nearest neighbor atoms. We neglected completely the next nearest hopping and the next nearest hopping as well. So actually, we need very fine tuning of the system parameters to obtain this perfect flat band. So this flat band is just very extreme cases or very special choice of system parameters. But still, there are many popular flat band systems people consider, like checkerboard lattice, where we have a flat band at the bottom, which is also touching with another band at the other symmetric point. And in the relief lattice, we have also a flat band in the middle due to the chiral symmetry. And it has also band crossing, which is linear in this case with the other bands at the gamma point. And also this one is called the scale lattice bilayer. Actually, I designed this model for some reason I will talk about. And this also has a flat band at the top. And this is a really simple model. And this also has a touching point at the gamma point. But I will show you this band touching is very different from other models I just introduced. Okay, so there are many flat band models. And people have studied these flat band models because they are interesting. So why they are interesting? So
sorry, Jun-Won. We have a question from Dario. Yeah. Dario, please go ahead.
Okay.
You can unmute yourself.
Who? Okay.
Dario Rosa.
Yeah, I will. Sorry,
Do you have a question, Dario?
I cannot unmute him.
No. I think he can unmute himself. So
okay.
All right, I think maybe we just carry on, maybe.
Yeah, okay, I will just first carry on.
Yeah, I think maybe it's just a false alarm. Let's carry on.
Okay, so so people have been interested. Hello?
Yeah, sorry, I couldn't unmute myself. That was my mistake. So now can you hear me?
Yeah, I can hear you.
Yeah, sorry, it's probably a very trivial question, so I apologize in advance. But is there a way, given a certain lattice, to guess if this lattice will develop flat bands or not? Or is just a hard, I mean, you just have to do the computation without any a priori guess?
So your question is, can we have a flat band in any kind of lattice system?
Well, let's say, suppose that I arrive with the lattice. Is it, how can I say, easy to guess from just by watching, just by looking the lattice, if this lattice can develop or not flat bands, or is something that you have to compute and then see?
That's a very good question. It's about the construction of a flat band, maybe it's related, but actually the lattice, underlying lattice structure is also important to have a flat band. But more important is the hopping structure.
I see.
So even in the scale lattice, we can have a flat band if we make very strange shape of a hopping structure.
I see. I see.
Yeah.
And there is some way to understand, let's say, a priori this, or is something that you observe by doing the computation?
Yeah, it's well-known fact is that, like the Kagome lattice, if we have some frustrated structure in some sense, I mean, if there is a spin up and down at these two sides, we have a frustration here. But this is, although this is for the spin language, but this structure makes electrons can have some kind of a destructive interference when they hop to this same side here. So it makes some localization. Some maybe later I can, after my talk finished, if you are interested in, I will talk about more detail, but this is quite important fundamental things in flat band systems.
Okay. Thank you.
Okay. Thank you. Okay, let me go on. So because of the zero Bloch velocity, we have also zero kinetic energy for the carriers in the flat band. So the kinetics of these charge carriers are extremely suppressed in the flat band systems. So the only important energy scale would be any kind of interaction in the system we are interested in, like the electron-electron interaction. So if the electron-electron interactions are the important energy scale, then we expect many-body ground states related to this interaction would be induced quite easily in compared to other band structures where we have a finite kinetic energies. So people wanted to solve some many-body problem in these flat band systems. And really, indeed, in historically, like people have studied ferromagnetism over the flat band by Tasaki, and also superconductivity from the flat band is also studied by Bloch, and also some Wigner crystal and other many interesting correlated physics have been discussed in the flat band systems. And most recently, actually, the flat band superconductivity was greatly highlighted due to the discovery of the twisted Bilayer graphene. So twisted Bilayer graphene is basically a graphene bilayer, but they are twisted to each other by an angle theta like this. And due to this twist, we have some superstructure from the lattice mismatch between those two layers. And they make very big super lattices. And at some spatial angle called magic angle, we have a nearly flat band at the Fermi level. And if we change carrier density, they found out the twisted bilayer graphene exhibit superconductivity as well as a mud insulator depending on the temperature and the carrier density. So recently the flat band business becomes very big due to this discovery. So this is why people studying flat band systems. So let me move on to our motivation. Up to now, I just talked about why flat bands are interesting. And actually, my question was more simple, actually, than this complex many-body physics, actually. So my question was, so what happens if we apply magnetic field to the flat band? In other words, what is the Landau level structure of the flat band? I actually asked this question to my colleagues, and they, from their very simple-minded classical idea like me, they said because flat bands has infinite mass, they would not respond to the external field, so nothing interesting will be found in the flat band's Landau levels. So actually, this is quite reasonable in the our quantum mechanical knowledge, because we know from quantum mechanics that parabolic bands, we have Landau levels with equal spacing, where the energy spacing is the h bar omega c, which is called cyclotron energy. And this is actually inversely proportional to the effective mass, as we all know. And actually, flat bands is extreme case of this parabolic band with infinite effective mass. This means that the cyclotron energy corresponding to this flat band would be 0. So Landau levels do not show any discrete energy levels, and they are all degenerate at the same energy of a flat band. So in this quantum mechanical point of view, flat band's Landau level would be also really no interesting. Yeah. But we are talking about solid state physics, not the classical mechanics or quantum mechanics. We should talk about this periodic array of atoms, and the Landau levels of such a complex system is well analyzed by Onsager's semiclassical quantization rule, which is described by this single equation, where S0 is the semi-classical orbit's area at the energy epsilon. So we have a band structure in the momentum space, and at the energy level epsilon, and we have an energy cut. So there is a cross section in the band structure, and we can have a semi-classical orbit, which is the bound of this cross section. And the area inside of this closed orbit is called the semi-classical orbit's area S0. So this is quantized. This is studied by Onsager. And here, this is the quantization rule given by integer number n here. And there is some constant due to quantum correction. And gamma is the Berry phase quantity. So this is the Berry phase along this path of the closed orbit. So if we put all those informations, because of this quantization, we have quantized the energy levels. The energy satisfying these relations are only allowed. So in this way, if we increase n, we obtain different semi-classical orbit at higher energy with a discrete energy gap. And yeah, so in this way we have in this way we have Landau levels corresponding to those semi-classical, allowed semi-classical orbits like this. This is what we do by using Onsager's semi-classical quantization rule to obtain Landau level in the Landau levels in the solid state. Okay, but in flat band, this Onsager's semi-classical quantization rule cannot be applied actually, because we have any kind of semi-classical orbits in the flat bands, because they are all at the same energy like this. So the S0, the semi-classical orbit, is not unique in the flat band cases. So this very popular quantization rule cannot be applied to our flat band systems. So using this simple-minded classical idea, we have a very boring conclusions, and this well-known Onsager's semi-classical rule, we have no clear conclusions. So we just try to solve this problem directly by using quantum mechanics. Okay, so we considered two examples. So first one is the square lattice bilayer, where we have a flat band on top, and we solve this problem under the magnetic field exactly. And the right-hand side is the Landau levels of this system. You can see there are equally spaced Landau levels in the middle, corresponding to this quadratic part of this dispersive band in the lower band. And the flat band is at the energy equal to 2. Okay, so we should look at this region to see how the Landau levels of the flat bands looks like. And if we zoom in, you can see actually nothing happens. All the Landau levels from the flat bands are degenerate at the same energy of the flat band as expected from the simple-minded point of view. So in this square lattice bilayer case, really the Landau levels of flat bands are really boring. But in the cogmal lattice case, it's quite different. You can see in this case, flat bands is at the 0 energy, and the right-hand side is the full Landau levels of the cogmal lattice. And you can see there is an equal spacing Landau levels due to the quadratic part of the upper dispersive band. And at the 0 energy, there is a Landau levels corresponding to this flat band. So if we zoom in, you can see in this case, we have something new. Actually, for me, it was really shocking, because Landau levels are developed in the gap region below the flat band. You see in the original band structure, below the 0 energy, we have nothing. According to conventional point of view, like the Onsager's quantization rule, we cannot have Landau levels in the gap region. This is very strictly forbidden, but in the cogmal lattice case, very strangely, we have Landau levels in the gap region like this. We express this kind of behavior as a Landau level spreading. Okay, the Landau levels are spread into the gap region. And we want to understand why this kind of Landau level spreading is happened, and how to understand this magnitude of this Landau level spreading. Okay, so maybe the starting point, a good starting point, is to answer what is the difference between those two flat band models, square lattice bilayer and cogmal lattice. So what is difference between them? Because in the band structure level, they look very similar. They have a flat band. Okay.
Jun-Won, sorry, another question by Dario. Go ahead, Dario.
Okay.
Yeah, I mean, can you go to the previous slide?
Yes.
Yeah, I mean, it looked that the Landau levels are somehow geometrically spaced, right? I mean, the spacing have a geometric progression, right? I mean, do you understand it? Eh?
Yeah, it's depending. It's proportional to 1/n.
Okay, do you
when-
understand this analytically, or is an observation? I mean,
I can explain the reason why we have a 1/n in the later part of my slide.
okay, thank you. Okay, I will wait then.
Yeah, please.
Thanks.
Okay.
Let me add another question.
Yeah.
So in this Kagome case, what is the degeneracy level of each of these flat bands? Can you quickly comment on that?
Sorry, what is the general?
Degeneracy level of each of the flat bands. When you switch your magnetic field off, you will have, if you have a flat band, you will have a flat band normally with a degeneracy level which is equal to the number of unit cells. Right. Now, what happens here? What is the degeneracy level of each of these bands? Is it still equal to the number of the unit cells, or is it different?
Yeah, it's a good question. And actually, at each Landau level, like this E naught, the bottom Landau level, the Landau level degeneracy is exactly the same as the usual conventional Landau levels, like 1/2 pi L scale, where L is the magnetic length. And
no. Look, let's say you have a volume. Let's not talk about magnetic lengths and these things. You have a lattice with some boundary conditions, but you have a 2D lattice, so you have a certain number of unit cells.
Yes, yes.
Okay, and now my question is, what is the how is the degeneracy level of these bands related to the number of unit cells you have?
So basically, if we have an n number of degeneracies at the flat band before applying magnetic field, we have exactly the same number of states if we sum all the possible states in this all the Landau levels.
Yes, but in one, how many are there in one?
How many?
Yes, let's take E naught. Let's take the energy E naught, the lowest.
I think
Landau level. So what? How many states are in there?
Let me see. So, you know, when we solve a half zero problem, we quantify the magnetic flux pi as one of maybe P over Q, where P and Q are integer. In this case, we have if we set P equal to 1, we have a Q number of bands. So at each Landau level, we have energy states equal to n over Q, where Q is 1/pi. So at each Landau level, we have n multiplied by magnetic flux pi per unit cell. That's exact statement.
Well, it cannot be larger than n, right? So n is the total number of unit cells.
No, pi is okay.
So if you switch your magnetic field off, all this fine structure collapses into the good old flat band, right? So that flat band had originally n, let's call it n, capital N, had degeneracy of level capital N, where capital N simply equals to the number of unit cells. Yeah. Well, actually it's n plus 2, but that's maybe not so important, I hope at least. Maybe it is. Now you switch on a magnetic field, and for a particular setting of flux choice, etc., you get this structure of these Landau levels. And now all the states must still be in there. So each of these Landau levels has now a much lower level of degeneracy than the previous flat band. And my question is, if that's right, then what is the level of degeneracy?
Maybe you are talking about very large magnetic flux, like more than one? Or
I'm talking about your picture, which you show here.
Yeah.
Nothing else.
Yeah, it's n multiplied by phi, I can say. Yeah, it's smaller than n usually.
This cannot be. This cannot be. If it is, if each of these Landau levels has a level of degeneracy of the order of the volume of your whole system, and you have an infinite number of them, as it looks like, then there is something wrong with the counting.
There is, in this case, we don't have an infinite number of Landau levels, actually.
Well, because you have a finite lattice, I understand.
Yeah, yeah.
No?
There's a finite Landau levels when we solve lattice model. Yeah.
Really? So you have an infinite lattice and you have a finite number of Landau levels.
Infinite lattice, it's depending on the magnetic flux, actually. So if we solve a continuum model, we have an infinite Landau levels approaching this zero energy. But when we solve a half zero problem, by definition, we cannot have an infinite number of magnetic bands. The magnetic bands, number of magnetic bands are restricted to 1 over pi, actually, right? So when the phi is 1 over q, we only have a q number of magnetic bands. And that is the number of Landau levels in that case. Is it answer for you?
So you always have a finite number of these levels, which you show here.
Yeah, yeah. I always have a finite Landau levels for a given magnetic flux. So when we increase the magnetic, when we decrease the magnetic field close to 0, then we obtain more and more Landau levels.
Sure. So, but then there's a finite number, therefore there is no true degeneracy, say like 1 over n, like it was indicated before in the discussion. So there's simply a finite number of bands. It's not seen from the figure simply. That's.
But when we increase n, then the states at each Landau level will also increase proportional to that.
Okay,
yeah.
Thank you.
Yeah, thank you. Very tough, tough questions. Okay, let me move on. So again, my question was, what is the difference between those two flat bands? Okay, and actually, to answer this question, I should, sorry, time. Okay, I should introduce the concept of a singular flat band as well as the quantum distance. So let me spend some time to explain those two concepts. So the singularity in the flat band, actually the difference between those two models is that in the first case, like the square lattice bilayer flat band model, we don't have a singularity. I mean, at the touching point, we can determine the eigenvector of the flat band uniquely without any problem. Because if we solve this problem before applying magnetic field, the eigenvector of the flat band looks like this. This is just a constant independent of the crystal momentum. So at the touching point, it is very well defined along A or B directions. So in this case, there is no singularity or discontinuity. So in this case, we call this kind of flat band as the non-singular flat band. Okay, but in the Kagome lattice, the situation is very different. The eigenvector of the flat band looks like this in this case. You can see at the gamma point, at the touching point, you can see the form of each element is 0 over 0. So you cannot actually determine the value uniquely at the touching point. Indeed, along A direction and B direction, we obtain different value of the eigenvector. So this is the singularity I meant. So in this case, we call such a flat band as a singular flat band. So actually, those two models belong to different category. Okay. And I would like to explain a little bit more on this singular flat band. So in the singular flat band, actually, it is characterized by some real space topology, so-called non-contractible loop states. So in flat band, we have a compact localized states as a localized eigenmode. But in the singular flat band case, those compact localized states cannot form a complete set. This is what we shown very rigorously in our PRB paper. And because those compact localized states cannot form a complete set, we need to add more states to make a complete set to span the whole flat band. And they are found to be so-called non-contractible loop states, which are extended along one direction, but compactly localized along the other direction. So if we plot this non-contractible loop states in the torus geometry for our periodic boundary condition system, then you can see they are actually winding the torus geometry of the whole system along poloidal and toroidal direction. And actually, we cannot cut those topological states. They are very robust. So this is why we call this is topological states.
Sorry, Jun-Won. Dario, please go ahead.
Can you, because it looks that that this explanation that you are providing somehow is highly dependent on the boundary condition, and it looks to be a bit highly dependent on the fact that you are on a finite lattice. So can you comment about, let's say, when you go to the infinite n case in which the lattice becomes?
That's a really good question, and actually that is my next slide.
Okay.
So
sorry.
no, actually missing one figure, but the thing is that if we can actually make a finite system from this torus geometry by cutting this system along this direction and this direction. In this process, actually, we can have some guarantee that this existence of non-contractible loop states leads to this some kind of a boundary mode called the robust boundary mode. And this also has the same robustness. I mean, it cannot be cut easily. It just worked like this. And okay, so.
Okay, but if the lattice become infinite, this kind of mode somehow, what happened? I mean, if the lattice become infinite in all the spatial dimensions, right?
Yeah, right. So this is the case where the lattice is finite.
Okay, and in the infinite lattice system, you still have this this property, or you lose it because somehow this mode go to infinity?
You mean what property? Like
let's say, I mean, the fact that you have these Landau levels rely on the fact that you have this kind of modes, right? So what is the fate of these states when the lattice become infinite?
You mean Landau levels or this non-contractible loop states? Sorry.
Both, because as far as I understand, the presence of one of the two determines the presence of the other, right?
Actually, it's a little bit different story. Actually, this is just some auxiliary story. But Landau level case, in the finite system, we can still have the same structure. But there can be some edge mode between those Landau levels. But basically, we can see this Landau level spreading. And this non-contractible loop states is just for very artificial case, like a periodic boundary condition. But still, my point is that in the finite system, which can be made in real experiment, we can still observe the related topological states. That's my point. Yeah.
Okay, so let me just rephrase to see if I understand. You are saying that in the infinite dimensional case, in the infinite lattice case, you still have the Landau levels, but this explanation doesn't apply anymore.
Does not lie anymore? I mean,
does not apply anymore. I mean, you need another kind of explanation.
I got your point. Actually, because actually these topological loop states are not that closely related to the understanding of Landau levels. Actually, this is just for introduction to what is the singular flatband. And actually, for the Landau levels, I should introduce the quantum distance physics later.
Okay.
Sorry for the confusion. Yeah.
Okay. Okay. Thank you.
Let me use this and add another question. So say you take the Kagome lattice with the flat band which has a band touching.
Yep.
Now it is true that the flat band is different from the you call this the bilayer square lattice or square lattice bilayer model, but according to some other classifications of flat bands, the difference is simply that the square lattice bilayer hosts compact localized states which are of class U equal 1, meaning that they reside entirely within one unit cell.
Yes, exactly.
And therefore they form an orthonormal set. While in the Kagome case and in many other cases, the compact localized states occupy several unit cells and form, first of all, a non-orthogonal set. Now, in the particular fine-tuning case, when a non-orthogonal compact localized state set is touching a dispersive band, you get all these effects which you discussed right now, with compact localized lines and some interesting other topological things entering the game. However, it is possible, I would say, that you can take your Kagome lattice and detune all the hoppings in such a way that you will preserve the flat band and you will preserve the compact localized states occupying more than one unit cell, yet you will gap it away from the dispersive band. And if you do that, then the compact localized states or that flat band will be in some sense not anymore singular according to your discussion, but it will be still different from the flat band of the square lattice bilayer. Now, what happens in that case if you have studied that with the Landau levels, which you were which you are discussing? Will you still get a non-trivial fine structure of these Landau levels?
Yeah, that's a really good question. And actually, in our study, we only considered this flat band with touching. But if we have some gap, the basic model will be different. We need more parameter representing the gap size. So actually, this is beyond our study, actually. And actually, we left it as a next project, and we are studying this case exactly the same, the model, like a Kagome model with the gap. And actually, in this case, if I tell you the results very shortly, is that there is some structure gain. And this is due to the interband coupling. And this is also related to some kind of other kind of quantum geometry related to interband coupling, so-called some interband barrier connection. So actually, this is a quite different category from our study, where we have always band touching. In this case, we have a most simple 2x2 Hamiltonian. But when we introduce some gap, we need more parameter, and it is a different model, actually. Okay.
Thanks.
Yeah, thank you.
Sorry, there's another question. So, Sung-Jong, please.
I have a question. Does this
Sorry.
We cannot hear you very well.
Oh, does the singular and non-singular flat band categorization, does it have anything to do with the I guess I think in this case there's degeneracy at the singular point, so it may not be the case. But is there any way to connect it to the Chern number or like the magnetic monopole of that singular point?
That's also very good question. Actually, the Chern number is related to the Wannier obstruction, and Wannier functions are looks like very similar to our compact localized states of the flat band. So it seems like there is some connection. But the thing is that compact localized states are very different from one-year function in that they are not orthogonal to each other, and they are also eigenmode of the flat band. And my answer to your question is that actually there is some close relation. In the singular flat band, we cannot define the Chern number because there is a band crossing. But if we introduce some mass gap, we usually have a finite Chern number in the basic 2x2 language. But more general n by n Hamiltonian, in the singular flat band case, by gap opening, we can have a finite Chern number in very well chosen gap opening perturbation. But from the non-singular flat band, we actually cannot have a finite Chern number after some adiabatic change of the system. So the relation is that from singular flat band, we can have a finite Chern number nearly flat band in some choice of good perturbation. That would be my answer.
Okay, thank you.
Thank you. Okay, so let me move on.
Sorry, another question. Mengson, please go ahead.
Yes, can you hear me?
Yes.
Yes, so could you back to the previous slide? Okay, yes, this one. So I'm just curious that, so in this case, this singularity point which you touch with this flat band is a parabolic dispersion, right?
Yes.
And well, as far as I know, in Libre lattice, which you have this intersection with this flat band, which the vicinity dispersion is like graphene, which is like a Dirac cone.
Mm-hmm.
Is there any connect, or is the result is different, or is there anything related to the dispersion of this dispersive band with this touching point?
So your question is it also same for linear dispersion at the touching point?
Some other dispersion, yes.
Yeah, so in this story, like a correspondence between singular flat band and the non-contractible loop states, it doesn't matter what the dispersions at the touching point looks like. Even in the Lieb lattice, we also have some kind of a non-contractible loop state. And in other cases, if there is a touching, whatever the dispersion is given, like a quadratic or linear, we always have a non-contractible loop states if there is a singularity in the Bloch wave function. Yeah.
Okay.
Yeah.
Thank you. Thank you.
Okay, so I'll move on. Okay, so singularity guarantees this kind of a topological states in the real space. And actually these robust boundary modes are experimentally observed very recently by collaborating with a Chinese photonic lattice group led by Zigang Chen. And they made a photonic lattice by using this laser lighting technique. And this medium, the cross-section of this medium is the lattice, two-dimensional lattice structure, what we want to study. And this is the real lattice example. And in our study, we realized the Kagome lattice, and we checked that this robust boundary mode are really stable, and they are also robust against some perturbations like this. Okay, so this is the introduction of a singular flat band. And the next, I will introduce the quantum distance to understand the Landau levels of the flat bands. So again, this is for just a reminder that up to now, what we know is that if we have this quadratic band and flat band touching at a point, if the touching point is non-singular, we have a very boring Landau level, which are no spreading. But when we have a singular flat band, we have this kind of Landau level spreading. This is what we know up to now, and we want to know more about this Landau level spreading. I mean, what determines this magnitude of the Landau level spreading? That is my next slide. So it is related to the quantum distance, actually. So let me introduce what is the quantum distance. And this quantum distance is another gauge invariant, very good physical quantity, which is much more simpler than Berry curvature, actually. And but not that much highlighted compared to the Berry curvature. And this is the definition. So d square is the square of the quantum distance, and it is equal to 1 minus absolute square of the inner product between two Bloch wave function. More precisely, actually, Vk is not the Bloch wave function. It is the self-periodic part of the Bloch wave function. Okay, so at momentum k and k prime, we pick up two Bloch wave function, and we measure the distance, quantum mechanical distance between them by using this quantum distance definition. So for example, when the eigenvector at k and k prime are identical to each other, we call that their distance is equal to 0. They are close, maximally close to each other. But when the eigenvector at k and k prime are orthogonal, exactly orthogonal to each other, then we obtain the maximum value of the quantum distance equal to 1. So basically, the quantum distance is defined from 0 to 1. This is very strange definition, but actually this quantity is discussed by Michael Berry in his next original paper, yeah, but not that much got attention. Anyway, what we proposed is that actually we can measure the strength of the singularity. This sounds very strangely, but anyway, we want to define strength of the singularity at the touching point by using this quantum distance quantity. So we pick up arbitrary pair of k and k prime and measure the quantum distance between them and pick up the maximum value of them among all the quantum distances. And the maximum value of the quantum distance is our definition of the strength of the singularity. Okay, this is definition. And what we have found is that this quantum distance can be visualized vectorially by using pseudo-spin language. Because we are studying this two-band model, we can have naturally this pseudo-spin definition by using Pauli matrices. Okay, and then we set a very small circle around this touching point, and we draw the pseudo-spin along this circle like this. And what we found is that for the non-singular touching case, like the bilayer scale case, we found out that the pseudo-spins are aligned for all momentum. Okay, but in the singular case, we have found that the pseudo-spins are canted with respect to each other. This structure is exactly the same as we shrink the circle close to the touching point. So this is very robust feature of this 2x2 Hamiltonian 2x2 model. And in the maximally singular case, we can have this kind of a winding of the pseudo-spin as well. So except this very extreme special case, we usually have no winding, no topological structure, but we only have some canting structure. And actually,
sorry, Jun-Won, we have a question from Sung-Jung. Please go ahead. Sung-jung, you have a question?
I'm sorry. Sorry, I didn't unmute me. Does this, I mean, just by looking at the picture you showed here, I'm just wondering if there's any relationship with the Berry flux, local Berry flux at that point. Even we, exclude that singular point, we can do some kind of, very small circles, contour integral for closed loop, and find out the Berry flux. And Berry flux is going to say the change of the, local change of the phase of the wave function, right?
Yes.
And I guess it should have some relationship with this one.
Yeah, actually, that's another project we are working on. And one of our students in our group is working on that. And there's a really relationship between this canting and the Berry flux. Yeah.
So relationship is not that simple.
Quite simple, actually. Yeah, quite simple. But I cannot tell more. It's just a going on project, but it's a very good question. Yeah.
Even the previous definition of, like one in the previous slide, this one, the one minus that, definition of D squared, it seems they can also be rewritten as a form of the phase difference between VK and DK prime, right? So that's gonna give some
that will be answered in the later slide, actually. Yeah, I will quickly explain about that. Okay, thank you. Okay, so I introduced the two concepts, quantum distance and pseudo-spin. And by using pseudo-spin, we can also define the strength of the singularity in this way: the maximum canting angle among all the possible pairs of the pseudo-spins. So in the non-singular case, the maximum canting angle is equal to 0 because they are aligned. But in the general singular case, we can find maximum canting angle like this. And this is the definition of a strength of a singularity. So we have two definitions of a singularity strength. And actually, they are related to each other by this very simple relationship. So the figure D on the right-hand side is maybe the answer for Dr. Sung-jung Woo's question. So x-axis is the quantum distance, and y-axis is the canting angle between K and K prime. So actually, the quantum distance and the canting angle is are same concept. They can be exchanged. We can use both concepts equally. Okay. So in conclusion, we have a definition of strength of singularity in a very unified manner. So we can use maximum quantum distance as well as the maximum canting angle to define the strength of the singularity. Okay, so we are now equipped with all the information like the strength of the singularity by using the quantum distance or pseudo-spin and the singular flat band concept. So let me come back to our original results, this one. So our purpose is to understand how this magnitude of the Landau level spreading of the singular flat band is determined. So the right-hand side figure is our main slide, and this is the result. X-axis is the maximum quantum distance of the band crossing point from 0 to 1, and y-axis is the ratio between this Landau level spreading and the Landau level spacing of the upper quadratic band h bar omega c. The y-axis, I consider this kind of a quantity because I want to have a dimensionless quantity. And this ratio between Landau level spreading and the Landau level splitting is a very simple monotonic function of the maximum quantum distance like this. As you can see, these diamond markers are the numerical results for very arbitrary models. Although it looks like very simple, actually we have 9 parameters to describe this kind of a 2x2 Hamiltonian because it is a quadratic Hamiltonian. But whatever we have a random parameters for this flat band model, they are all in the universal monotonic single curve like this. And we found out this fitting function because we can analyze some extreme limits analytically. By using that, we obtain this fitting function. So really, this magnitude of the Landau level spreading is determined by this maximum value of the quantum distance. And by using this fitting function, actually, if we can measure the Landau level spreading by experiments, we can extract this quantum geometric quantity, the maximum value of the quantum distance, by using these results. So this is the main results, and actually quite numerical. But in the next slide, we have some analytic.
Sorry, I have a question again. So what is the red line again? Can you?
Red line is just a fitting function we found to because we cannot solve the problem fully analytically. We cannot obtain the curve describing this numerical results, but we found out that very nice fitting function.
What do you mean by nice? What is nice about
It's a very small error.
Okay. And how is that related to your previous discussion of connecting this quantum distance with this canting angle?
In this figure, it's just a numerical. In x-axis is the quantum distance.
Yes.
So, but
that's it. Yeah. Thank you.
Okay.
Got
so, yeah. Okay. So, so seeing the Landau levels of the flat band, we can extract the quantum distance. That is the main message of the this figure. And actually, we can have a little bit more intuition from the analytic results in the small d max region, this weakly singular case. In this case, we can solve the problem analytically. In this case, we can think the weakly singular Hamiltonian as the addition of the non-singular flat band model and small perturbation that gives the system singularity. In the non-singular flat band, as I explained, the Landau levels of the flat bands are at the same energy of the flat band like this, and the upper Landau levels are all from the quadratic band. But when we add singularity, these Landau levels are spread like this, and we can understand why this happened from the perspective of the quantum distance like this. So in this Hamiltonian, when we assume d max equal to 0, which corresponds to this non-singular case, we only have a diagonal term, which corresponds to the energy of this one and this one. Okay, but when we include the maximum quantum distance, and actually we have shown that this maximum quantum distance expresses the interband coupling between quadratic band and the flat band. So they put in this off-diagonal element like this. And we found out that those off-diagonal element is proportional to the d max. So the nature is actually very simple. It's just a level repulsion between the quadratic band's Landau level and the flat band Landau level due to the interband coupling encoded by this quantum distance quantity. And maybe one question in the very first part of the slides that why we have a 1/n dependence is because we have this coupling between quadratic Landau level and the flat band Landau level. And we can think of this coupling as some second perturbation results. That means it proportional to inverse of the energy difference between flat band and upper Landau level. And this difference is proportional to n. So when we do the perturbation theory, this Landau level spreading should be proportional to 1/n. So this is why we have a 1/n here. And in more elegant way, we can think of this is just a mirror image of the upper equally spaced Landau levels in the second order perturbation theory point of view. Okay. So this is some intuition why we have a Landau level spreading from the quantum distance point of view. Okay, and actually now I have explained all the fundamental features. Okay.
Yeah, sorry, I think Sung-Jong has yet another question. So Sung-Jong, yes, please.
I think Sung-Jong,
you need to unmute yourself.
Sorry. So it seems that like, I mean, the flat band itself for the non-singular flat band and singular flat band, they have different structure, even though we don't look at the quadratic band, right? But it seems that even though they are not the same, without the quadratic band, the spread is not going to happen. Is it right? So I mean, well, my question is the spreading. Is it only comes from the interaction between the quadratic band and the flat band, or the structure of the flat band itself?
It's coming from the interaction between quadratic band and flat band. And actually the Bloch wave function of the flat band is very tightly tied to the upper quadratic band. I mean, they are really entangled to each other. So actually in this singular case, we cannot tell this flat band separately. Do you got my point? So
okay.
I think it's yeah.
So without the quadratic band, it's not going to happen, right?
Right. That's right.
I see. Thank you.
Do you have a proof for that?
Yeah, basically the non-singular flat band.
No, this is not a proof. No, this is not a proof, because as we discussed before, I can take your Kagome lattice and I can determine the hoppings such that I will keep the flat band, I will make it gapped from the dispersive spectrum, but I will keep it distinctly different from this trivial U=1 case of the square lattice bilayer example. And it's not at all clear to me whether suddenly all your nice fine structure will collapse. I would actually bet my 5 cents on that it will be still there and that it is all related to the internal, well, essentially related to the internal properties of that flat band, which is a U=2, 3, or whatever you want to call it, flat band with non-orthogonal compact localized states.
Yes.
So then that's why I'm asking, and do you have a proof? I mean, I don't take the square lattice bilayer example as a proof, because that's a trivial
I understand.
problem.
I understand your point, and in my Nature paper, we don't have a proof for that statement, but in my ongoing project, actually, this interband coupling is always important. That is what I can say, maybe. You got it? Sorry, do you hear me?
Yeah, okay. Well, I mean, so we don't have a proof yet. Okay, good.
Yeah,
Thank
we
you.
don't have a proof exactly, but I'm quite sure that the interband coupling is really important.
Well, you always need it, right? I mean,
right.
Otherwise, if I would say if you remove all the other bands and you want just to leave one flat band, then you will always reduce this problem to a trivial U=1 flat band. That's all you can do.
Maybe
so
U=1 flat band,
which is not U=1. You will
I think so. Yeah.
You'll be forced to have to add also other dispersive or other dispersive bands.
Right.
And so they have to be there.
Right.
That's
Yeah.
correct. Yeah.
Yeah.
Sorry, perhaps related to the previous comment. I mean, if maybe I missed something, but if I understand correctly, the notion of singular and non-singular flatband is not intrinsic, right? I mean, rely on the how can I say, on the relationship between the quadratic part and the flatband part. If you don't have the quadratic piece, the notion of singular and non-singular collapse to be the same. Am I right? You don't
Sorry,
have the, how can I say,
I didn't get the.
In other words, the notion, I mean, the distinction between singular and non-singular flatband rely on the presence of the quadratic band, right? If you don't have the quadratic band,
really good point.
there is not such notion.
Yeah, exactly. So actually, quadratic band touching is very important here.
Exactly.
And,
exactly. So just the flat band, there is no distinction between the two situations, I guess.
Right. That's a really good point. And
no, but I don't agree with it. And this is the whole discussion we have right now. And we don't have an answer, but I'm almost betting that it is not that simple. Dario, so there are flat bands and flat bands. And even if you detach your flat band from some dispersive bands, you have different types of flat bands.
So probably you have to develop a, how can I say, a notion and an explanation that doesn't make use of this distinction, right?
Maybe Jun-Won is right. I don't know. Maybe he's right, but I'm just betting my 5 cents that there's more to that.
Yeah, there's more, and that is our ongoing project again. But this theory should be, I think, extended. This is just for very simple, the most simple case, I think, quadratic band touching. We found out it is the most simple case we can treat. And in other more general cases, we need some generalization. There is more.
The notion of singular and non-singular.
Yeah, within, beyond this simple classification.
Okay.
Yeah, very good questions. Okay, so yeah, there are lattice model realizations, because before I just showed the continuum model results for the quadratic band crossing with the flat band, but we tested various lattice models like Kagome lattice and checkerboard lattice, which all have this kind of singular band crossing, quadratic singular band crossing at the gamma point or X point here. And you can see this Landau level spreading, and also here Landau level spreading. And we found out that they are really determined by the maximum value of the quantum distance very well, and also shows 1/n dependence. And due to the 1/n dependence, we found out that the susceptibility, orbital magnetic susceptibility, diverges, because the susceptibility is the second derivative of the total energy below the Fermi level. And you see below the Fermi level, the energies are proportional to 1/n. This is the harmonic sum, which is diverging. So we naturally have a divergence of the orbital magnetic susceptibility. This is a very interesting mechanism to obtain divergence of the singularity, divergence of the susceptibility, so logarithmic. Okay, this is another interesting feature from the 1/n dependence. And for the realistic analysis or realization of our singular flatband, we found out several examples called cyclic graphene, cyclic graphene, and cyclic graphene. And they are all carbon network system in this shape. So from left to right, we make the size of unit time simultaneously. You can see the bandwidth of the singular flat band is smaller and smaller. And in this cyclic graphene case, we have a extremely small bandwidth. And maybe in this system, we can see the anomalous Landau levels of flat bands quite easily, but still, these are all still DFT calculations, and there have been no experimental synthesis examples for these systems. So I think it's quite challenging, but it would be interesting to check. Okay. So, okay, this is the summary. So basically for this quadratic band touching over the flat band, for the non-singular case, we have a no Landau level spreading, but in the singular flat band case, we have a Landau level spreading, which is sharp contrast to the Onsager's point of view. And we found out that this is due to the interband coupling, which is quantified by the maximum value of the quantum distance. And this is it. So thank you. Thank you for listening. And
yeah, thank you, Jun-Won, for this wonderful talk. We already had quite a few questions from the audience. Let's take another 1 or 2 quick questions if the audience still has. And the rest can be deferred to the discussion session after the talk. Okay, so let's see if there are any more hands up from the audience.
Can I ask?
Yeah, surely, please go ahead.
The fit with the parameters R and S. What are the values of R and S, and what led you to guess such a function?
Yeah, very good question. And R and S are, I forgot the exact number. One of them is smaller than 1, maybe R might be smaller than 1, maybe. But the C is determined from this value, where D max is maximized to 1, where we can solve the problem exactly, which actually corresponds to the Kagome lattice. So C is obtained exactly, and 3/40 is also obtained analytic analysis around this.
That I understood. I only didn't understand the R and the S.
Yeah, R and S is just some intuition, because at here we found out that the slope goes infinity. So I just guessed that to have such infinite slope here, there should be S, something like that. And R is from just a fitting parameter to some non-trivial dependence in between. Just like that, yeah.
Okay.
All right. I don't see any more raised hands. So if not, let's thank our speaker once again.
Thank you.
And with this, I think we officially end the PCS seminar. Let's take a 5 minutes break and come back for the participants who are interested for a discussion session, but after 5 minutes. So see you at the coffee place.
Okay, thank you.